Hello everyone. In this video I am going to derive expression for distribution function in case of Maxwell Boltzmann statistics. Okay, here we are going to consider an isolated system, that is isolated system. We already know that what is isolated system. Let us suppose here I am going to consider one system, and this system consists of number of particles, that is it consists of n number of particles, and the number of particles of entire system is constant. And one more thing, it is having energy capital E, that is energy of the entire system is denoted by capital E, and this E also constant, and there is no exchange of energy and number of particles between other system. This is the isolated system. And one more thing, let us suppose here I am going to consider different energy levels, that is this is E1 and second energy level is E2 and E3, so on EI. EI is the ith energy level, and here E is the total energy of the system, and E1, E2, E3 and up to EI are the individual energy levels. And let us suppose there are N1 particles which are having energy E1, that is let us suppose if we consider a system, it consists of many atoms, and in these atoms some of the atoms are having energy E1s, that is some of the particles may have energy E1 and some of the particles may have energy E2, and we denote these particles by N2, and some of the particles may have energy E3 and we denote these particles by N3, and the particles those have energy EI are denoted by Ni, and capital N be the total number of particles of the isolated system, and these two are constant. But here one more thing, the energy levels, that is E1, E2, E3 are the first, second, third level, and EI is the ith energy state. Here the energy of each level is fixed and the energy is constant, but the number of particles, that is N1, N2, N3, Ni may change, because let us suppose if you consider these three particles are having, let us suppose these three particles have energy E1, and any one these particles may collide with this particle, and some of its energy is transferred to this atom, and the particle gets more energy and shifts to the higher energy level. Let us suppose if it jumps to E2, then the number of particles those have energy E1 are 2. So here number of particles are not constant, they are variable. Here energy is constant but the number of particles are variables. One more thing we need to know that, let us suppose E1 splits into two or more levels, that is if it splits into two or more levels or quantum states, and we call this energy levels as a degenerate levels. We call these levels as a degenerate levels, and we denote it by G1. And in same way, let us suppose second level is split into two or more levels or two or more degenerate levels. Degenerate means same energy level is split into two or more different energy levels, but these energy levels are having same energy. Let us suppose this is E1 is the energy and these two levels are going to have same energy. This is the degenerate level. Here also same, we denote it by G2, and let us suppose EI is splits into two or more degenerate levels, then we denote it by GI. G1, G2, G3 up to GI are the degenerate states, that is same level splits into two or more energy levels. Okay, now let us derive expression for Maxwell Boltzmann statistics. Here we are going to write the first equation is that the total number of the particle, that is capital N, which is equals to the number of particles present in E1, the number of particles present in E2, and so on. Capital N is equals to N1 plus N2 plus N3 plus so on up to Ni, and we can write this expression as a summation of Ni. And one more thing, here total capital N is equals to summation Ni. Let us differentiate above equation, that is if we differentiate this equation we are going to get dN is equals to summation dNi, but here the total number of the particle of entire system is constant, so dN is equals to 0, so it becomes summation of dNi is equals to 0, or we can write summation dNi is equals to 0. Let us denote this equation by 1. Now let us write the second equation, that is energy. E is the total energy of the system, and which is equals to the number of particles. Let us suppose N1 be the number of particles which are having energy E1, so which is equals to N1 E1, and N2 particles are having energy E2 plus N2 E2, and so on the particles which are having energy EI Ni, so on plus Ni EI. Let us differentiate above equation. Differentiating above equation, we get dE is equals to, here E is constant and N1 is variable, that is number of particles are variables and energy is constant, so here we get E1 dN1 plus E2 dN2 plus so on EI dNi. But we know that energy of the isolated system is constant, so dE becomes 0. So above equation becomes E1 dN1 plus E2 dN2 plus so on EI dNi, which is equals to 0, or we can write this equation as a summation of EI dNi, which is equals to 0, and let us denote this equation by 2. Now let us arrange, that is let us arrange the number of particles the number of ways in which the group of n1, n2, n3 so on up to ni particles can be chosen from particles here, and this expression is given by W1 represents the number of ways in which the particles can be arranged, which is equals to capital N factorial divided by N1 factorial, N2 factorial, N3 factorial, so on. Let us know how this expression came. Here, what I am going to do, let us suppose arrange N1 particles out of capital N, and we can write this expression as NC N1. This is the combination of total number of particles to number of particles which are having energy E1, and we can write it as a n factorial divided by n minus n1 factorial into n1 factorial. In this way we can arrange n1 particles in different energy levels. That is, we know that there are different energy levels, that is E1, E2, E3 so on up to EI are the energy levels, and we can arrange these n1 particles out of total number of particles in different energy levels in this way. It gives the number of ways in which n1 particles can be arranged in these energy levels, and also arrange n2 particles out of n minus n1. That is, out of these particles we need to arrange n2 particles in different energy levels, and we can write these arrangements by n minus n1 C n2, which gives n minus n1 factorial divided by n minus n1 minus n2 factorial into n2 factorial. Or we can write for all particles, that is W is equals to, or W1 is equals to n factorial divided by n minus n1 factorial n1 factorial into n minus n1 factorial divided by n minus n1 minus n2 factorial into n2 factorial, and so on. Here n minus n minus n1 gets cancelled, and similarly in next term n minus n1 minus n2 is going to cancel, and this will continue. Then we are going to get n factorial divided by n1 factorial, n2 factorial, n3 factorial, so on. Or we can write it as a n factorial product of ni factorial. This is the W1. That is the number of ways in which group of particles, that is n1, n2, n3 up to ni particles, can be chosen from total n particles and arrange them in different energy levels. Okay, now Ni particles can be distributed in Gi superscript Ni ways. Then the total number of arrangements would be W2 is equals to G1 power N1 G2 whole power N2 G3 whole power N3 so on Gi whole power Ni, or we can write it as a product of Gi power Ni. Here I will try to explain how this equation we have written. Here I am going to explain it by taking example. Let us suppose here I am going to consider degenerate state, that is E1 is a degenerate state. It is having two energy levels and there are two particles A and B, and I am going to arrange these two particles in these two levels. That is, this is the first way and this is second way, third way, and this is the fourth way. In four ways we can arrange these two particles in these degenerate states. Or let us suppose if same energy level is having three energy levels, that is three same quantum states, and then if you need to arrange these two particles in these three different states, here we can arrange first one AB, or AB, or we can arrange it as a B or AB, or finally AB. Totally here we can arrange 1, 2, 3, 4, 5, 6, 7, 8, 9. In 9 ways we can arrange these particles, and here in 4 ways we can arrange two particles in 2 levels. Here in 9 ways we can arrange two particles in 3 levels in Maxwell Boltzmann statistics. Here we can write it as a 2 square, and here we can write it as a 3 square. That is, here 2 represents number of states and here 2 represent superscript 2 represents number of particles. Here also same, 3 represents number of states and 2 represents number of particles. In general, here we can write it as a number of states superscript number of particles. For energy level E1 we can write it as a, here G1 is the degenerate state and N1 is the number of particles. So we can write it as a G1 whole power N1 for E1 state, and similarly we can write for E2 G2 N2, and also similarly for third energy level we can write it as a G3 N3, and so on. For ith level we can write it as a Gi Ni. We represent it by W2. W2 gives the Ni particles can be distributed in Gi states, or it gives the number of arrangements. Now we have written these two equations. Now let us write the number of ways in which N, that is total number of particles, can be arranged among the possible energy levels is W is equals to W1 into W2. It gives the total number of arrangement is equals to N factorial, N1 factorial, N2 factorial, N3 factorial into G1, N1, G2 whole power N2, and so on. And we denote this equation by phi.